Welcome back to INST 314, Statistics for Information Science. I'm your host, Shawn Janzen, and we're wrapping up the module on one sample Z&T hypothesis testing with the last topic, 8.6, on effect size and power. So let's go ahead and talk about the effect sizes and powers specifically for Z's and T tests. Now, before we talked about effect sizes that I gave you for chi-squares, and those are the phi and Kramer's V. Now we're going to talk about Cohen's D. Cohen's D is the mean effect size for Z's and T's. It's a standardized statistic that talks about how far your mean of your observation is from the mean of your null. Now, because it's standardized, that means it's unitless. It doesn't have units such as pounds, miles, inches, number of dogs, etc. Okay, and Cohen's D is not affected by the number of observations. The formula for Cohen's D is D equals the absolute value of x bar minus mu divided by sigma, where x bar is your sample mean, mu is the null hypothesis population mean, and sigma is the null hypothesis population standard deviation. Again, it's in an absolute value form. If we want to go ahead and look at this and how we go ahead and calculate it in terms of interpreting our Cohen's D, we're going to use our French fry size before with the small, medium, and large, but the numbers are changing a little bit. Now, Cohen's D is considered small at 0.2, it's medium at 0.5, and large at 0.8. These values are different than the small, medium, and large from your chi-square, phi, and Kramer's V, so I recommend that you go ahead and keep maybe a note chart so you know when you look at a particular measure for effect size, you're looking to see the right sizes of small, medium, and large for them. And before we go into an example, I do just want to mention that the Cohen's D is your standardized effect size, but you can still have the unstandardized effect. That is where you get to keep on the particular units. And that is really just looking at what is the difference between your observed mean and your population mean. What is that actual amount difference, if it's in dollars or dogs or whatever it is you're measuring? That's the unstandardized amount. The difference was dividing by sigma and then also the absolute value. So let's go into an example here where we're talking about University of Maryland's freshmen and their SAT scores. You've read in a newspaper that the mean SAT score for a nation's high school graduates is 500 with a standard deviation of 110. You think that University of Maryland freshmen have higher SAT scores on average than the nation's high school graduates. So to find out, you randomly select 100 University of Maryland freshmen and find out their SAT scores. And on average, they had an SAT score of 535. So let's go ahead and plug this into a by-hand Cohen's D, and we have the mu of 500. That was the average, nation's average for the SATs. Our sigma was 110. That was the nation's standard deviation for those test scores. Our sample size is 100. X bar was our sample SAT score from the freshman, was 533, and we're going to do an alpha two-tailed test. We go ahead and plug this in, and note, I don't really need alpha or the n value here when we're doing this test. We only need x bar, mu, and sigma. And when I go ahead and put it out, I get a D score equal to 0.3, and that is the difference between the average University of Maryland student and the national average. And this is relatively small, 0.3 standard deviations. This is a measure in standard deviations from that mean. Now, small was 0.2, medium was 0.5. It's relatively closer to small, which is why I said this is small. These are soft rules when you're talking about small, medium, and large, so just kind of take that in stride. Now, if you're talking about Cohen's D as a mean effect size in R, we can go ahead and calculate this out, but you need to install the package LSR. Once you install LSR, you can run a library on it, and that's going to give you access to the Cohen's D function. Note, Cohen's is in lowercase, and a capital D for Cohen's D. Then we input x and mu, where x is the average and then mu is the average from it. So we go ahead and in this case, we need, and when you specify x, x has to be a vector of data. So using the Cohen's D in our approach, we're going to flip back to our GPA example that we had before. And I already had a vector of data from a sample of 117 students where we checked their GPA to see if they were going to be different from the education departments at GPA. And so in this case, I specify Cohen's D. I put in GPA as the vector of data, comma, mu equals 2.7, and that tells me I get a Cohen's D of 0.389. Now, if I was to go out and try and do this by hand, I would use a mean of GPA, gives me a 2.96, a standard deviation of 0.68, and if I went and put this into a by hand sort of approach, doing an absolute value of 2.96 minus 2.7 divided by 68, it's going to give me a D score of 0.382, which is very close to what we would be getting by using the function there. Now let's talk about proportions for effect sizes in R. Now in this case we're going to use Cohen's H. D was for means, H is for proportions. And H is a non-directional magnitude of difference, so it's just talking about an overall difference from one to the other. Now in this case we're going to turn to the power package, okay? And that's going to give us a function called ES in capital dot H. Capital E, capital S dot lower h. In parentheses we're going to give it the P sub S from our sample and P sub U of our population. If you want, you could do this in the ugly version with a by hand formula, which I'm putting on the screen here for you below, but that's going to be using asymptotes and a few other components that, you know, we need a little bit more math than you need for this course in general in order to work out with a by hand approach, but it will give you an approximate value. Now if we go ahead and plug this in with our Maryland voting example here, I would define P's, in this case I have P1 and P2, but they equate out to the 0.56 and the 0.5, and that's going to give us an Cohen's H of 0.12. If I put those same values in with the ugly version formula, it gives me an identical value there. So capital ES dot lower h is a much friendlier version to go ahead and get your proportions effect sizes. Let's switch gears and talk about power. Power for one and sample t-tests generally works the same as how we were dealing it with the chi-square. We're still going to use the power functions, but instead now of using W, we're going to use D for the mean effect size, or H for the proportions effect size. And the power concept of how we're talking about power, meaning we're going to have accurate results if we reject or fail to reject the null hypothesis, remains similar. We're going to reference functions from the power package, and we're going to have three different functions for this. If you're doing a one sample Z, your function is pwr.norm.test. If you're doing a one sample T, it's pwr.t.test. And if you're doing proportions, it's pwr.p.test. All of them are the same except what goes in the middle of the dots, norm, T, or P, depending if you're doing Z, T, or proportion testings. And to show you an example of how we're working with this, we can go ahead and say, what is the power of the study we conducted on the University of Maryland's freshmen's SAT scores? So in this case, I'm doing pwr.norm.test. D was equal to 0.3 because I want to see the effect size that we had, and the N sample size we had was 100. Sig levels are alpha 0.05. Null is what I'm indicating for power because I want to find out what is the power, and I'm doing the two-sided test, meaning it was a two-tail. When I run that, it tells me my power is 0.85. So I have about an 85% power rate here to see that I have an 85% chance to correctly reject the null if the null should be rejected, or fail to reject the null if the null should have been rejected. So that's what we're getting at with there. If I want to switch this to do a t-test version, I'm going to do the same results here and plug all this in, except I'm doing power.t.test, and I get a power of 0.84. And if I want to switch this up to do an example for the Maryland voting, I'm going to go ahead and plug these in. And in this case, for H, I'm just going to use the es.h formulas. I could go ahead and just take the effect size that I had before, but I want to show you as well that you can go ahead and plug in a formula to give the effect size in case you didn't want to have to run it by hand separately. And I have a power of 0.527. Now this power is far below our expectation desired value of 0.8. So I would draw into question the Maryland's voting example if I want to make sure that I have results that are certain about them. And just briefly, I want to introduce you to this cool little concept that we can actually do power plots. Now, you can go ahead and take your entire power test, save it as an object. In this case, I'm doing the norm, T, and proportions tests, and I'm saving them as power test 1, power test 2, and power test 3. And on each of them, put them inside of a plot function. So I'm doing plot of power.test1, plot of power.test2, and plot of power.test3. And what they will generate for you, on the screen here, we're looking at the power plots for the Z's and the T's. And so what we can see here is it's showing us the sample size that you're going to need at a given power level. And the dotted line that shows the optimal, that's showing the N that we specified. So we can see how does our power go up as our sample size increases, given the effect size, the alpha, and the tails portions that we put into the test. And on this next slide here, I'm going to show you how it looks like for the proportions. I just couldn't fit all of them onto the slide with all three of them together so they could look good for you. So I split them up. This one is the proportions, and the other ones were the means. And so this is a great little tool just to kind of show you how does your power increase as your sample size increases, holding constant the tails of the test, the effect size of the test, and the alpha level. And with that, I'm going to go ahead and wrap up our talk on one sample Z and T testing, and I'll see you all in the next module where we start our topic on two sample Z and T testing.